afternoon, students. Today we are going to discuss about a very important topic about refractory period. Before that, I will discuss a quick summary of what was taken in the last video, action potential. So it is very easy. Here this diagram represents the action potential of a neuron. Resting membrane potential is minus 70 millivolt, and you can see here threshold is minus 55 millivolt. Once the threshold is reached, this phase is called depolarization phase, and you know the reason for depolarization phase is sodium influx. So plus is coming in. Because of that, this phase is D for depolarization phase. This minus 55 is coming to plus 30. This plus 30 millivolt is spike potential. Then once it reaches the spike potential, again there is a R, repolarization phase. This is because of potassium efflux. So plus is going out, potassium is going out. As plus is going out, again the potential is coming back, plus 30. So anyway, once action potential starts, it has to end. So it is starting from RMP, resting membrane potential of minus 70 millivolt. Threshold is minus 55 millivolt. Firing starts here, reaches the spike potential. Potassium efflux is causing repolarization phase. It is coming down, but we expect here to end at minus 70 millivolt the repolarization phase, but it still continues down. Just listen, the potassium efflux, the repolarization phase is still going down beyond minus 70, and again it comes back to minus 70. Now my question is, what is the cause H? What is the cause for this hyperpolarization phase? That is why the action potential curve starts from minus 70. We expect it to end at minus 70, but it is not ending. It is going down below minus 70. What is the reason for, just see my hand, what is the reason for this hyperpolarization phase, which we already discussed. So you can pause the video and try to find out the answer, the cause for this hyperpolarization phase. Okay, hope you found out the answer by pausing the video. The reason for this hyperpolarization phase is potassium channels are very slow to open and close. So they are very slow to close. So what happens here? Still some potassium channels are open. Here also open. So what happens? Still potassium is going out even after reaching minus 70 millivolt because of slow nature of potassium channels. Voltage gated potassium channels are slow to close. So as it's not yet closed, some potassium is coming out. So because of that, minus 70, minus 80, minus 90. Now it is coming back to minus 70 from here. Maybe this is minus 90. So my second question, why or how this minus 90 is again coming back to resting membrane potential of minus 70. So again you can pause the video and try to answer how the potential is coming back to minus 70. I hope you would have found out the answer. Yes, the reason is sodium potassium pump, one of the reason. Like genesis of resting membrane potential. In my previous video, I would have clearly explained how RMP is being formed. So the sodium potassium pump brings back the resting membrane potential again to minus 70. So this is the complete action potential curve. So starting from minus 70 millivolt, and this is the action potential of a neuron, remember. So what I am explaining is action potential of a neuron. So starts at minus 70 millivolts and ends at minus 70 millivolts. Today's topic, we are going to discuss about refractory period, very important period, which comes in the action potential curve. So what is refractory? Refractory means not responding to anything, obvious. So period. So refractory period means in this action potential curve, there is a period during which if I give a stimulus, there will be no action potential. For example, if I am giving a stimulus here, second stimulus in fact. So if I give a second stimulus is here, and the second stimulus is not producing any extra action potential curve, that means this is refractory period. So refractory period means the period during which if I give a second stimulus, that second stimulus will not produce any extra curve, or the curve will not respond to any second stimulus. That is called refractory period. Now again, to add to the confusion, there are two types of refractory period. Absolute refractory period, relative refractory period. I hope now you know absolute. Absolute means absolute. So during this absolute refractory period, when I am going to give a second stimulus, to to the already going action potential curve, this up down, depolarization, repolarization, depolarization, repolarization. During this curve, if I give the second stimulus, there will be no response at all. No response. The curve as usual goes, whatever second stimulus I give, it will not respond. That period is called absolute refractory period. Not at all, no response. Relative refractory period means during that period, during that relative refractory period, if I give the second stimulus, there is a possibility of increase in the curve of this action potential, but the normal stimulus will not be enough. For example, here minus 55 millivolt, the threshold, there is a depolarization phase. That potential will not be enough during the relative refractory period. When the curve falls under the relative refractory period, in that relative refractory period, if I give a strong stimulus, an action potential can develop. Strong stimulus, the second stimulus which I am giving should be very strong. In that relative refractory period, if I give the strong stimulus, I may get an action potential curve. Whereas in absolute refractory period, even if I give a strong stimulus, strongest stimulus, no response. So that difference to understand. Now let's come to the main topic. In this action potential curve, you know all the bases. The reason for depolarization, repolarization, hyperpolarization, coming back to resting membrane potential. So now I am going to tell which is the absolute refractory period in this curve, which is the relative refractory period in this curve. Before going to that, I would like to teach you the basic mechanism of the voltage gated sodium and potassium channels which are linked to this action potential curve, so that you can yourself tell which is absolute refractory period, which phase is relative refractory period. So I will draw the diagram. So in this action potential curve, to know which is up to which is absolute refractory period, up to what is relative refractory period, I will first tell the periods. Just note it down. Up to 1/3 of repolarization. So this is repolarization phase. Just understand the depolarization phase and up to 1/3. Very, very important. So note it down. Absolute refractory period is the period during which when the second stimulus is given, no response. The second stimulus will not be able to elicit another action potential, or even it will not be able to increase the strength of the action potential curve. No response. Now up to 1/3 of repolarization. So now this is relative refractive period. So relative refractive period starts from after 1/3 or the last 2/3 of repolarization phase and hyperpolarization phase. Note it down. So relative refractive period is the period, the remaining 2/3 of repolarization phase and hyperpolarization phase. So in this, for example, here, if I give second stimulus, the same strength of minus 55, like if I give a normal second stimulus, what will happen? Nothing will happen because it is RP, refractive period. But if I give a stronger second stimulus, yeah, I can elicit action potential because this is relative, not absolute. Now we are going to see why up to this is absolute refractive period. First we will go step by step. So the entire depolarization phase and the 1/3 of repolarization phase is absolute refractive period. So see the concept. Yeah, now see here. The red color one is voltage gated sodium channel. The green color one is voltage gated potassium channel. So here what's happened? The sodium channel gates are closed. So here the gate is closed, no sodium influx. But see here, just concentrate please. The voltage gated sodium channel is closed. You can see that closed. This is, yeah, you can see here it is closed. So nothing can enter it. Potassium channel is also closed. But once the threshold is reached, minus 50 millivolt, firing starts, which we know. So this is the initial phase of depolarization. This is the final phase of depolarization. So sodium influx starts here. Sodium influx. Why sodium influx occurs? See the gate. The gate has opened. So here the gates opened. Sodium channel influx. So the sodium channel gate is opened here. So sodium is coming in. Whereas potassium channel gate is still closed. So because of sodium influx, sodium coming in plus, this is coming up to plus 30 milli. Now listen here. So up to plus 30 is the spike potential. So yeah, here also what happens, the sodium gate is open. So sodium influx. This entire depolarization phase is sodium influx. Sodium keeps on coming in. Now why this is absolute refractive period. Yeah, up to this is absolute refractive period. Why this depolarization is absolute refractive period? Yeah, you see here. Already the sodium, this is like a gate. So already the gate is open. And once it reaches here, it is fully open. So when the gate is already open, how can I still open it? I can't open the gate which is already open. That is very, very important. So it is already fully open. The sodium voltage capture channels are already open. The sodium influx is occurring. So that is the basis behind this absolute refractive period. Now coming to repolarization. Okay, you can think depolarization, sodium influx. So already sodium is coming in. I can't further push in. Or already the gates are fully open. I can't open the already open gate. Accepted. Now coming to this repolarization phase. Potassium efflux. Potassium is going out. See the condition of the sodium channel. What happens? Yeah, the gate is closed here. So you can see here. This is like a lock. Like here. The sodium gets what happens? The gate, this one, the inactivation gate, which is here, is now locked, is now coming back to block it. Now can I put sodium? Now you imagine, here the second stimulus. Yeah, I am now giving the second stimulus here. So, I am giving second stimulus with the absolute refractive period, that is up to 1/3 of repolarization phase. This you will again repeat. In this phase, when I give second stimulus, nothing will happen. Because already sodium influx has occurred, already the gates are open. I can't open the gate, it is already open. Clear? In this phase, first of 1/3 of repolarization phase, see the condition of the sodium gate. Yeah, it is locked. So it is locked. So again, if I am giving the second stimulus, sodium influx is not going to occur. Because you can see here, the inactivation gate has come and locked it. So this has to open, then only sodium influx can occur. So here it is locked. The sodium gate is locked. So sodium influx cannot occur. So the absolute refractive period is from the depolarization phase up to 1/3 of repolarization phase. Now coming to relative refractive period. Why? I call this as relative refractive period. So now what happens as the potassium efflux here? Again, the potassium efflux has started. See here during depolarization phase, potassium gate is closed. Here also the RMP starting of the action potential curve, the potassium gate is closed. Now coming to the 2/3 of repolarization phase. What happens? You see here. Yeah, the lock has opened. You can see here. The inactivation gate is coming out, or almost similar to this. See this diagram and this diagram, the sodium. Yeah. So this lock has come out as the potential decreases. Now imagine, if I give second stimulus, yes, there is a possibility when I give second stimulus, because of the force, there is possibility for me to open this gate, or this can happen like this. This can occur like this. So this can occur like this here. Yeah, but the second stimulus should be strong. If you want to answer, you can pause and answer. My question is, yeah, actually the gate is like this. So if I give a second stimulus, I can convert from this to this. So I can try to make the sodium activation get open. But the stimulus should be stronger. The second stimulus should be stronger. You can pause the video and try to answer. Why the second stimulus should be stronger in this phase? To elicit a second response. Yes, the reason is, here the potassium channels is open and potassium efflux is occurring. So already one process is going, potassium efflux is occurring. But I still want more sodium to come in against the repolarization phase. So against the repolarization phase, already potassium efflux is going. Along with that, I am trying to bring in sodium. So obviously the force which I need is more, or the second stimulus should be stronger than the first stimulus. For example, here sodium influx is occurring. So whatever stimulus I give here, I have to give more stimulus than that for relative refractive period. So relative refractive period, definitely if I give second stimulus, I can generate another action potential, or I can increase the action potential curve, but the stimulus should be stronger. Why the stimulus should be stronger? Because already potassium efflux is occurring, and if I want the sodium influx to occur, I have to give more force. So now I hope you are very clear. Absolute refractive period is up to 1/3 of repolarization phase, where whatever strong the stimulus, however strong the stimulus I give, no response at all. Relative refractive period is, yeah, this is also relative refractive period. Even hyperpolarization also the same scenario. even hyperpolarization phase and 2/3 of repolarization phase. The sodium activation gate is closed, but I can open it if I give a second strong stimulus. That is relative refractive period. So in today's video, I started with the various phases of action potential curve, and I discussed about what is absolute refractive period, what is relative refractive period, and which phase is absolute refractive period, which phase is relative refractive period. And I also explained the mechanism behind it. So we'll meet in next class. Thank you.